Finding an equation from a graph of a polynomial. Like we did with the graphs of quadratic functions, we can spot some features of a polynomial to help us make an equation. Given this graph, h of x, we can set up the function equation similarly to how we did with quadratic functions. With those quadratic functions, we had the vertex form of an equation and solved for the leading coefficient using a point. We will do the same now, but instead of the vertex of a parabola, we will use the x-intercepts and suspected multiplicities of the graph. This function has a 0 with a multiplicity of 2 at x equals -1, a 0 with multiplicity 1 at x equals +1, and the graph shows another x-intercept at +3. This x-intercept crosses through the x-axis but behaves differently than the 0 of multiplicity 1. The 0 at x equals +3 has multiplicity 3. We'll write this out as h of x equals a times x plus 1 squared times x minus 1 times x minus 3 cubed. We can't use the x-intercepts for our extra point, so we'll estimate using something else, say the point 0, 27. When we replace x with 0 and h of x with 27, we can solve so that the leading coefficient is +1. This looks accurate since the end behavior goes to positive infinity on both ends. Our h of x is x plus 1 squared times x minus 1 times x minus 3 cubed. We can leave it in factored form. This was an example of finding a fully factored polynomial and leading coefficient from the graph's x-intercepts. You can extend this thought process to finding the equation of a polynomial based on a description or table, or finding a rational equation from given information.